Hello everyone. Today I'm going to introduce CLAN, exploring continuous learning on commodity edge devices using asynchronous distributed neuroevolution. As we look towards the future, the edge seems to become more and more important as it grows at an exponential rate. The future of AI really lies at the edge, where its true power can be realized as it finds more and more applications. The edge devices are not only expected to grow rapidly in number, but also are expected to grow much smarter. So it is important that we examine the AI at edge landscape. Today, training is performed at the cloud. The edge device collects and sends the data to the cloud, where a data engineer labels and structures this data to perform training at a high-performance cluster, and an updated model is then sent back to the edge to perform inference. But is this model really scalable and suitable to keep up with the pace at which the edge devices seems to be growing? Which brings us to the challenges of the current landscape. The first being the limited uplink and downlink bandwidth to the cloud. As devices at the edge grow, the sheer volume of data collected to be processed will make it difficult and expensive, could choke the limited bandwidth and increase latency. Secondly, it is likely that not all edge devices will be able to have connectivity to the cloud in their deployment environments. So, as edge devices find more and more application, concerns about privacy and security of data are bound to increase, which may not be addressable at the cloud. The solution to this seems to be to perform training at the edge. So now let's take a look at training at the edge and its challenges. The first major challenge with training at the edge is the widely different deployment scenarios and rapidly changing environments. The solution is to not only be able to perform the task well in different environments, but also to be able to acquire new skills to overcome challenges. That is continuous learning. Another challenge with performing training at the edge is the limited compute and memory budget of edge devices. Any learning algorithm chosen needs to be able to be fit in this limited budget of hardware resources. Data processing poses another challenge, as there is a lack of any mechanism to label and structure the data to perform training. So when we look at supervised deep learning that needs well-labeled datasets, manual hyperparameter tuning, and is designed by a scientist for a single problem, along with the very expensive backpropagation based training where activations from the forward pass need to be stored for the backward pass, it makes supervised DL a poor fit to perform continuous learning at the edge. To select an algorithm for continuous learning, we first really need to know what continuous learning really looks like and what does it really need. So in an environment, an inference agent performs an action and receives a reward. These accumulated rewards are then sent to the learning algorithm, which provides an updated topology or weights or both to the inference agent, and this process repeats itself. This is how you can learn how to improve at one task or even learn multiple tasks. This learning algorithm looks a lot like reinforcement learning. Could reinforcement learning be the answer to continuous learning? Although reinforcement learning can work with unlabeled datasets and continue to change based on how well it performs a task with the flexibility of reward functions, the reliance on backpropagation based training and manual hyperparameter tuning means that reinforcement learning is not viable for continuous learning at the edge. Here we turn our attention to neuroevolutionary algorithms, which are also very similar to reinforcement learning. We take a look at neuroevolution of augmented topologies, also called as NEAT, as an example of neuroevolutionary algorithms. In NEAT, we start with an initial population of genomes. Genomes are neural networks that are expressed as a graph, and each edge and vertex of the genome is called as a gene. Our next step is to evaluate the population fitness by performing inference. We then ask if the desired fitness was achieved. If not, we move on to the next step of evolution, which is learning, to reproduce the next generation, and we keep performing this cycle until we achieve the desired fitness. But how does NEAT really achieve this evolution and make sure that each genome, generation after generation, is performing better? To do that, it creates a parent pool of the fittest individuals of the previous generation. It then chooses two of the parents and performs a genetic algorithm using crossovers and mutations like adding connections, deleting connections, adding nodes, so on, to perform reproduction and form the offspring. Once it has formed enough offspring, it performs speciation. Now, NEAT introduced speciation to be able to group different individuals of the population into buckets. The reason NEAT does that is to ensure that the species which are in its very early stages of developing useful features to solve the problem are not killed off by species which are fitter right now. This gives NEAT a larger search space and prevents stalling of progress due to local maximas. So could neuroevolutionary algorithms be the answer to continuous learning? Neuroevolutionary algorithms can not only work on unlabeled data and be flexible using reward functions, just like reinforcement learning, they can also work with automatic hyperparameter tuning, and most importantly, the absence of backpropagation means that the memory footprint of neuroevolutionary algorithms is drastically smaller. Additionally, the very independent tasks of performing inference of each individual in the population and reproducing offspring gives us massive parallelism, which is good for compute. We also have to ask if continuous learning is enough. Edge devices are often deployed in groups across many application fields such as enterprise, agriculture, or industries. Could we transfer the knowledge gained by one unit to help the entire system? It is wasteful for each individual to learn how to solve the same problem from scratch. Performing distributed collaborative learning is the obvious next step. So, to achieve this, could we scale NEAT? We already saw that NEAT could be a suitable candidate for continuous learning, but could we scale NEAT to perform distributed collaborative learning as well? To check this, we set up a test bed with 15 Raspberry Pi units for our tests, which are connected with a local Wi-Fi network to each other. We used the NEAT Python repository and 6 OpenAI Gym environments as our choice of workloads. We chose 2 small workloads, Carpool and Mountain Car, 1 medium-sized workload, Lunar Lander, and 3 large workloads, the RAM games. We also only update the fitness function between the workloads and run all the workloads till convergence or failure with the maximum time steps of 200 between each generation. This is the multi-step inference. We also test single-step inference where the generation is updated after each action. So let us look at some of the design choices we made while distributing NEAT and the evaluations. Looking at NEAT, the process of evaluating fitness, that is inference, is a completely independent task which can be done in parallel, but each genome performs independently. Therefore, we select this as our first step to scale NEAT on our distributed system. We take a look at such a scenario where there's a central agent which performs all 3 tasks of inference, reproduction, and speciation, and the distributed agents only perform inference. The central agent creates a new population, it speciates that population, and then distributes the genomes across multiple inference agents. This inference is then performed in parallel, and all the agents reply back with the fitness values of their respective genomes. The central agent then selects the fittest parents, creates the pool, and then performs reproduction to form the next generation. And then we repeat the cycle to go generation after generation. Now, looking at our evaluations from distributing inference, we can clearly see that for medium and large size workloads, we scale inference pretty well. But for smaller workloads, we see that scaling stops at a certain point. Looking closely at Carpool, we see that the reason for that is the cost of communication over time tends to overcome the benefit from scaling, since for smaller size workloads, compute is not that much. So, our obvious next step to look at where else can we improve this scalability of this algorithm is the next parallel step of reproduction. In such a scenario, where the central agent performs all 3 actions and the distributed agents perform inference and reproduction, The central agent starts by creating a new population, speciates the population, and distributes the genomes across the agents, just like before. An inference is performed, and the compute agents will reply with the fitness values. The central agent then just selects the fittest parents and decides how many children are to be formed for each species. But instead of performing reproduction for the entire population, it distributes the parent genomes and the spawn count for reproduction. And now this reproduction is performed in parallel by all the compute agents. While inference is being performed in parallel, the question remains that what about speciation? Since we know that in need to speciate, you need to see the genome structure of all the genomes in the population. This information is not present with the central agent. So all the compute agents have to send these child genomes back to the central agent for speciation, and then the central agent speciates the population, and we can continue the cycle. There is clearly a problem with this design that is evident with the increased amount of communication overhead involved. Compared with inference, which is run up to 200 time steps between each generation in multi-step inference, evolution is much smaller in compute. Added communication overhead is an even bigger problem for scaling evolution, and this is clearly seen in our results. Across the entire suite of workloads, evolution fails to scale at all due to the heavy amount of communication costs involved. The majority of this cost comes from the transfer of child genomes that is done to perform speciation. If we could perform speciation on the devices independently without having to communicate with the central agent, we could solve this problem. So we next look at distributing the step of speciation. In this scenario, we have the central agent and the distributed agents, each performing inference, reproduction, and speciation. Starts by central agent creating a new population as always. Central agent then distributes the genomes across the compute agents, and then the compute agents perform speciation in parallel only on the subsection of the population they each received. Then they perform inference and reply back with the fitness values and the species ID to the central agent. The central agent can now then decide which species should form how many children, and this is then communicated to each agent, which perform reproduction in parallel and continue the cycle. This all-important step of performing speciation in parallel, we call it as asynchronous neuroevolution. Looking at the results, we can see that this design can scale evolution despite its low compute for the larger workloads, due to the much smaller communication overhead. However, as we grow the scale, the trend starts to reverse. It is therefore a question to ask whether at some point simple distributed inference performs better than asynchronous neuroevolution. To do so, we needed to go beyond our test bed of 15 Raspberry Pis and extrapolate our results further. So we extrapolated our results to the scale of 100 nodes for air-raid RAM to check this, and we plotted communication, evolution, inference, and the totalation time per generation. For multi-step inference, the compute of inference and its scaling overshadows any increase in evolution, and the scaling stagnates at around 50 units, but with asynchronous speciation performing better throughout the scale. When we look at single-step inference, the much harder problem, the performance improvement stops much earlier at 10 units, but again, asynchronous speciation continues to perform better for a much larger scale. Deploying massive intelligence at the edge also needs another metric evaluated, which is the price per performance, that is perf per dollar. Therefore, we compare our distributed system to two localized implementations, one on an HPC machine with a CPU and a GPU, and two on a Jetson TX2 board, both with a CPU and a GPU. Although our distributed system of Raspberry Pi units cannot match the HPC machine on any of the workloads, it matches the Jetson for the larger workloads at scale, delivering a price performance product improvement of more than 5x. So, in conclusion, we demonstrate a system of agents running on Raspberry Pis learning collaboratively using neuroevolutionary algorithms. The proposed modifications to the algorithm that we make allow scaling to continue up to 65 Raspberry Pi nodes. It shows a 2x performance improvement over the naive scaling and reduces communication overhead by 3.6x. The proposed system using cheap Raspberry Pi hardware can also outperform higher-end computing platforms, showcasing a price-performance product benefit of 2.5x. Thank you.